Or to the cloud. It is getting the screen that tells you. I think I can, it's recording, everything's set up here. It's happy. I can get rid of this too. But that's good. I'm happy with that. All right. Then there's 2 papers. I'll find them here. It's actually 3 papers. Only one of them. I think there's only questions about one of them. This other thing is this software. So all these simulations, there's going to be some, they're using some kind of software, like LAMPS is one, LAMMPS. That's kind of also molecular dynamics simulation. There's Blue, what is it, HOMED Blue. This is from the University of Michigan. That's another one. Those are the 2 that Polymer people usually use. LAMPS is by far the most popular. That was written at Sandia and Albuquerque, the nuclear bomb guys. But they also have like the largest supercomputer in the world or something. So they can do some kind of war games. But they've written the software to do all this dynamics simulations, you know. So like GROMACS is a really odd choice. This guy uses GROMACS to model polymers. So it's really odd because GROMACS is for molecular biology. I tried to find like, if you do that somewhere in here, you'll see like pictures like this, right? So it's just
When I was a student, I'd write long essays that I'd work on for days, but now I'm writing short.
here. So it's going to be pictures of these proteins.
It's okay.
I haven't looked at this before. I just want to see the picture that they get out of it. They simulate da 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 da, and then they end up with a picture of a protein, like that thing. So that's what GROMACS does. Those are like some kind of protein active site or something. And this is a virus. That's a COVID-19 virus at the bottom. So GROMACS like simulates that. You put in the molecular structure, and it's good because it has built-in water. Water is like the hard thing because water will structure. You know, so you can get the protein interactions, like all the molecules in the protein interacting with each other. But it turns out like the water, when it gets near, like when water gets near oil, it organizes, right? And there's a lot of water molecules compared to the protein molecules, like maybe 10,000 times as many. And the entropy doesn't depend on how big, it depends on how many. Right? It's going to be log of the number of states. So the water, the entropy of a biosystem is like all the water, right? And the free energy is the entropy and the enthalpy. So it's kind of like without modeling the water, you can't get what these structures are, right? So GROMACS is good at getting the water right. So that's kind of the main thing, that the difference between synthetic polymers where you don't have organization of the solvent around the polymer chain and biopolymers where you do, you know. So anyway, but the one thing nice about GROMACS is that when you see these proteins will form, like 2 main things that they form is the alpha helix and a beta sheet. Those are the 2 main structures, and those are usually assembled into some other thing, and eventually you get to something like this wheel, right? So anyway, to tell if you have alpha helix or beta sheet, you look at the dihedral angle. So as you go down the bond, so right, this is where this will get interesting. So you go to .cam, send a web, send a project. I get it now, I think. Hopefully this will work. So if you, all right, so mostly we're talking about vinyl polymers. So that's basically starts with a double bond. So if you don't know chemistry, this is like, or this might not help, but so this is kind of something that you're looking at, right? So this is called unsaturated bond because you can break it. So you can, so, and a single bond is saturated, so That would have like 3. Carbon is basically, think of it as a tripod with a flagpole, right? So it's kind of like tetrahedron, right? So basically, vinyl, you can have some R group here. So if it's polyethylene, the R group is H. If it's polypropylene, it's CH3. If it's polybutylene 1, it's an ethyl here, the CH2 like that, right? So 1 because that's the 1 bond. You could have the double bond in the middle. That would be butylene 2, and then that would make. I'm not sure you can polymerize that, but can you polymerize that, Mike?
One from polymers, 118, 119.
Yeah, because the 2 won't polymerize. Okay, so the reason it won't polymerize is the same reason that polypropylene until 1955 you couldn't polymerize polypropylene. So when you distill crude oil, then at the top of the distillation column you have ethylene, you know, that guy, and propylene are like, I think that's 80% of it. So half of it you threw away because you couldn't polymerize it. So it's just a waste product. The reason you can't polymerize it is because it's got resonance structure. So you have like this thing, and then it transitions to that thing. So they can flip back and forth. So if you make a free radical on that, so you take an electron off this, and then you have this thing, that can stabilize with this thing. You know? So basically, when you try to polymerize it, you go to grab this thing, and then it goes there, it runs away. So you can't get it. Right. So in 1955, German Ziegler found you could take like titanium TiCl4 tickel and mix it with aluminum oxide. So tickel was used in World War I as a nerve gas. It's like when you see the battlefield and there's smoke all over the place. That's because they're spraying TiCl4. So you take titanium, which is sand, put it in HCl, and you get TiCl4 out of it right away. Right? So anyway, so it's an easy chemical to make. The advantage is it made HCl, so it burned everyone alive. And it made the smoke, so it made it like battlefield confusion. So it was like a perfect weapon. You know? So they just dumped it all over Europe. Everywhere there was a trench. Anyway, so that was around, you know, and they knew how to make it. They made it industrial scale. They still make it industrial scale. You can mix it with this alumina oxide, organic, and then you can make this TiALO something structure, right? And what it did was, this is a transition metal. Somehow it can hold on to this propylene, like hook it so that it can't do that resonance anymore. So it just sticks in that one thing. Then you can make polypropylene, which is like water bottle caps, or like basically every plastic. So 80% of all plastics are high density polyethylene or isotactic polypropylene. So when you do this, we do that polymerization because you're holding on to it. The handedness of the addition is fixed. So you get isotactic polypropylene. Okay, and then there's some other options. So this brings up like tacticity. Okay, so basically, if you have the carbon atom and it's a flagpole, then I can put a polymer on 2 parts of it, right? Then I'm walking down the polymer. I'm short. I'm going that way, and I can either put the side group as the flag, so like left, or I can put it to the right. But I can't, you know, so basically there's a choice when you get here. So these are bonds that can swing around, right? So you can't like draw a picture of this except in 3D. If you look at it, you couldn't really tell the difference, right? But the polymer knows the difference because it's going to form a helix from that. So it's got to, if it's always in the same, if you always go left, 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 right? So 2 of those together is called a dyad. And if it's left, left, or if it's right, right, that's called a mesodiol dyad. Right? And if it's left, right, or right, left, that's a racemic dyad. So this is like mixed, and this is same or whatever. Right? So there's 2 choices of dyads. You can say, well, I can describe everything with dyads. So it'd be great, but there's no way to measure dyads. Okay, so the way to measure tacticity is with NMR, right? So you come in literally with a radio frequency like 700 WLW. That has the energy to kind of, it's like, so the smaller you get, the less the energy, right? So it's got the energy to kind of perturb the magnetic moment of the nucleus of an atom. So it's not like the IR is a lower energy is affecting the electron, or higher energy is affecting the electrons in the bonds, right? In Raman, and then X-ray is like even higher, it's ionizing things. So this is really low energy. So if you have a material and a really strong magnetic field, the nuclei actually orient their spins that have a magnetic field. And this radio wave is the energy of like kicking one of those spins. So it precesses. So it's a spinning proton. It's got a magnetic field. And then this radio wave is just the energy to kick that. So it precesses, that tilts, right? You can, when it does that, it decays back and gives off another radio wave. So 700 WLW comes back, and you can pick that up. Like you can pick it up with the same thing that you transmitted it with. You have kind of one antenna there, right? So anyway, so you have your chain with these methyl groups on it for propylene. Right? So you have a carbon, and then every other one has a methyl. And then you can look at like the protons here. So you look at the nuclei that have these magnetic moments, which are protons. So you look at the proton here, and it can look like that way and that way equally. This would be an any here. Right? So it can only do groupings of 3 or odd numbers. So the shorter, you can't get a dyad as a grouping of 2. You can't get that. There's no way to get it. The only way to get it is a group of 3. So that's called a triad, or you can get a group of 5. It's a pentad, or you can get a heptad. So the bigger the magnetic field you put on the NMR, you get this with a super magnet, like liquid helium or something, whatever. So superconductor magnets, you get bigger and bigger magnets, cost more and more. It's like the NMRs we have in the chemistry department are like $1.5 million each. You can get them for like 10 million. So you can get a really big magnet. And then you can see more and more of these tacticity units. You can see like with a cheap one, like the original one that you can build in your garage. I knew a guy that built one in his garage. He was at University of New Mexico. I was actually at Sandia for a while, but anyway, so he built one in his garage, and he had it. He was a professor at UNM, and he had it there. Like he had this NMR that he built, and he could get like triads, with that thing. It had fixed magnets, right? And then, but if you get these, you can get pentads and heptads. So you want to know more and more because he's going to give the thing a kick. So when the bond, so as you rotate about the bond, so you could say there's this dihedral angle, which is this kind of bond rotation angle. So as you're kind of looking down, well, if you're looking at the flagpole, right? So you can spin this thing around, like so you can say what's the energy on that. So you can do a Newman projection. So you can do like looking down the chain. So you kind of eyeballing down the chain. And then you have this kind of setup. So you have like carbon 1, carbon 2. So this circle is carbon 1, and it's got the tripod sticking off like that. That isn't there. And the middle one is carbon 2. It's got that tripod sitting off. And one of these is a polymer. The other one's a polymer. So that would be a planar zigzag conformation. So then you have your hydrogens. So one's going to be just hydrogen, the other one's going to be methyl. Right. So you can spin this guy around, and you can get the potential energy. I'm going to call that 5. So, and then when it's in this setup with PP over here, that's going to be like a minimum energy. And then the next is going to be methyl over hydrogen, and hydrogen over polymer, and polymer and hydrogen. So that's a little bit higher energy. So this is called a trans state. That's a gauche minus. That's a gauche plus. Then there's going to be the worst case when it's polymer. So it's going to be really high energy. So it's going to be this kind of setup, and this is a dihedral angle. Right, and there's two of them for the chain. You have like this one, and then there's another one. I think he calls it, what do you call it in there? Theta or something? Not theta. That's yeah. Calls this some other angle. I don't remember what it is. It's called theta. So anyway, you can spin both of those, right? And then you can say like what kind of helical structure you're going to get, and then basically this energy diagram changes with the tacticity of this thing, because the next group will matter, like the Polymer group will matter too. Right. So if you get the right arrangement, it'll form a helix. Right. And if you get, so there's three ways you can regularly space these things. Okay, so in terms of triads. So you can have meso, right? So you're talking about two dyads makes a triad. So you have one monomer, and then the next monomer, and you have to have the other two. Right? You have their methyl groups. Right, like that. So and because of NMR, you're kind of looking at that proton, so you're looking in both directions, so you get the three. Right. So anyway, so one way is that they're meso. So this is a dyad, that's a dyad. So they're like meso. That means they're the same. I'll make these me instead of M. Right. So that's isotactic. And then the other one is that they could be racemic. So it goes like left, right, left. Right. So that's symbiotactic. So that's MR or RM. And the other one would be, let's see, no, that would be RR, WRR, sorry. In other words, it's opposite, so it's RR. So it goes like left, right, left. And the other one's MR, which could be MR or RM. So there's twice as many of those, and that's hetero. Hetero means like mixed tacticity, mixed dyads, right? So anyway, so there's, if you had something called atactic, so you could have doesn't have tacticity, so you call it atactic. Right, so atactic in terms of dyads is 50% M, 50% R. Right. That would be an atactic without tacticity. It would be a random tacticity. Right, for triads, it's going to be one MM, one RR, so it would be like 25% iso, 25% symbio, and 50% racemic, because racemic can be in two different ways. So this becomes like one of those triangle things. So you have like, what's it called? Some guy's triangle, 1, 2, 1. Pascal's triangle, yeah. See, my brain is fried. Not that I could ever remember that, even before the 60s or whatever, hang on, but so it's going to go like that, and it's going to just keep going, right? So it'll be pentads, heptads. So you can see this becomes like a statistician's like wonderland, right? So how many like dyads? All right, so dyads aren't going to do you much good, because you could have a 50-50 atactic dyad polymer. There was a block copolymer, isotactic and symbiotactic. It would be 100% crystalline. Or you could have a 50-50 racemic meso, so atactic polymer that's totally amorphous because it's actually mixed. Right, so it depends on the distribution. The distribution you need depends on what you want to know. Right, so if you want to know about crystallinity, you're talking about crystal thickness of 100 angstrom, 10 nanometers, right? And your units are going to be something like 10 angstroms. So you're talking about a 10 unit sequence that you need. So you need a heptad nonad, I guess. You need a nonad, which means you need to pay $5 million for your NMR, maybe 10 million, right? So So in that case, you know, the unit that crystallizes, right? It all has to be helical. If you have one that doesn't, the crystal ends there. Right, so you get weird. Anyway, so the tacticity is important. Luckily, with the Ziegler-Natta catalyst, you can get perfect tacticity. It's always isotactic. And you can play around. There's metallocene catalysts now, there's others. Ziegler-Natta won the Nobel Prize for that because that was like a coup. That was all the stuff they were just burning and dumping. You could turn into like gold. You could take the dirt, actually your garbage, and turn it to gold. Right, yeah.
Sorry, can you just repeat one more time what you said about which subunit is crystallizing? Like at what point the polymer crystallizes? Or
So
why?
all right, the polymer is just this wormy thing, right? That's not going to easily crystallize. Sometimes it could, maybe it couldn't, but this tacticity matters. So it's going to go from that to form a helix. That helix can easily crystallize because it's already a helix. You just line them up. So they'll crystallize, right? They'll make this chain folded crystal. So that's the idea, just like the helix is the basis for the crystal. For polyethylene, the helix is the simplest helix. It's actually in the plane of the paper. It's like that's actually a polyethylene. And then the H's stick out, but the backbone is a planar zigzag. If you stick a methyl group on that, it gives it a kink. Like this energy diagram isn't symmetric anymore. So when it tries to form that planar zigzag, it can't do it. It has to move out of the way a little bit. And it does that the same way every time, and it makes a helix. Right. And it's a different helix if you have butylene. So you could have an ethyl here instead of methyl. That's this polybutylene thing. So I think that's a lot less of interest. How much polybutylene? You use it for stuff, adhesive.
I've never worked.
Mike works at Lyondell, so he knows.
Never worked with polybutylene. Work with polypropylene.
They use it as an additive, like an adhesive, I think, or something or other. So it's used, but I think it's because it isn't really in when you distill oil, it's not there. Like you have to make it. So it's going to be a lot more expensive. Right? So the other things are just there. You're just throwing them away. It's garbage. It's actually a pain. Like, what do you do with it? Right. So it's making CO2 when you burn it. So Ziegler-Natta, like, it was a great thing that they could figure this out. So Ziegler was a chemist and Natta was an Italian. But he was a diffraction person. He figured out this helical structure and how the thing worked, kind of how the catalyst worked. So they shared the Nobel Prize. I think it's partly political, like they want to give Nobel Prizes out to different countries, you know. And Italy was short or something. But anyway, Natta worked at that Lyondell plant in Italy in what's the town's name? Ferrara. I've been there. That place is cool. It's got like a castle and a moat and stuff. It's a really nice place. Then you go right to the outskirts of the town, and there's like a huge chemical plant. You know, so it's really like dichotomy. Also in the book Catch-22, that's the city that they bombed. They bombed Ferrara. Yeah, it's a really cool place. So anyway, and Natta had his lab there and stuff too. So it's kind of got history to it. Anyway, so that's that business. So hopefully you got some feel for that. So you want to get more, and you'll see in papers that have like MMR, like all the possible combinations of dyads to get whatever, to get higher and higher order, you know, to say what's going to happen. So it's of importance to the petrochemical industry. I see. You just got to do all of them. Huh? So these guys. So this has been. So, all right, if you look in the notes, which I don't have up, I guess I can add that here. Let me just go to that. Yeah, I'm sure I did. I don't know how to check. I guess I could just, yeah, I definitely did, you know.
I get that little guy up in the kind of top right corner. That's like a square with like a triangle.
It's really frustrating when like I can't understand at all what you're talking about.
Yeah,
This,
that's a lot.
this thing. All right.
Yeah, he's got it.
All right. Anyway, So I just wanted to bring up the PowerPoint of this thing. Actually, what if I just run PowerPoint? What? Okay, right here. It's probably still on the desktop somewhere, but let me get this up. Okay, so if you look in here, there's papers, okay, old papers where they look at these bottle brush polymers that I think I mentioned, but in passing, but. Right, so they're down, 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 down. So here, so these are all like computer simulations for bottle brush polymers. Make it this plot, right? So they're just a polymer with side groups. They change how long the side groups are, what the spacings are. And again, like this is the index of the chain. So you start at 0, it's a 100-unit chain. And it's got these side groups on it of different lengths or something. And if you get to the middle, you get a high persistence at the edges, because the edges flop around, they have a lower persistence, right? So anyway, so these simulations are done with something called coarse grain. So it's a Monte Carlo simulation, but it's a coarse grain. It can also be a molecular dynamics simulation, coarse grain. So what it means is there's no polymer at all. It's just balls with springs connecting them. That's it, right? And they just make side chain balls with springs. So that's called a coarse grain simulation. But you can't do, if you have balls and springs, you can't do tacticity, because you need to have like this handedness stuff, and balls don't have that. Right? So anyway, so they have to do an atomic scale simulation for this thing. Now let me go back here. So they can't use that coarse grain, which would be the first choice of anybody, because it's so simple. You know, so it's going to be absolutely the simplest thing you could do. So they use this kind of complicated Romex program because they want to get this kind of mapping of dihedral angles. So they can say, so if it's syntactic or isotactic, it has a different helical structure, right? And one is like a left-handed. So these helices are going to, they're chirality. So you have like right hand, left hand, like your thumb and then your fingers. So the two things are different, right? So, and in biology, they're really important. Like all your proteins won't, your enzymes and things won't function unless they're the right chirality. Everything is chirality in biology, right? So, and in this like discussion about what the first, like all alpha helices have the same handedness, right? And there's some discussion about why, like what decided that in the first place. But if you have the wrong handedness, and you just die, you know. So basically, this handedness seems like an insignificant feature, but it could be life and death. So anyway, left and right. So because you can map those two angles, you map them against each other. This is a density of the populations of the angles, and that can tell you if the helix is left and right. And only Gromax will give you these plots. That's why I use Gromax. Right, so it's kind of interesting, and it gives, can make a nice T-shirt out of the thing too. But anyway, so that's one point, and then the other point. So he goes through this business. Okay, like overview of what he did. He used Gromax, so that's really odd, right? And then all atom means he's not saying they're coarse grain. He's saying he's actually taken every atom in the molecule, which polyethylene and polypropylene and this polybutylene one don't have that many atoms. So it's not that big of a deal, right? And then he uses this OPLS force field, which is it's a combination. So you can just Google these things. Like Wikipedia is the best source in the world, I believe. So this is the OPLS force field. So it's the energy. So he's going to be calculating the energy of the system, right? And then the energy of the system. So here, let's just say this over in DocCam again. All right. So energy is KT. So it's the temperature. Right, so he's doing these simulations, and he's got a thing called a thermostat. So he takes like, he says his temperature is 100 degrees C or 373 K, right? And then he says he's going to calculate the energy of the system by taking his things, which will be polymer units or atoms. And he's going to kick them. They'll have a velocity, they'll have an acceleration, they'll have a position, right? So that's molecular dynamics. Everything in the system has a velocity, acceleration, and position. Then there's these force fields. The force field, as I was showing you, it's going to decide what's the consequence of that motion. And then the energy is like a half mv squared. So if he's got the velocity, he's got the energy, he's got the temperature, but he has his temperature that he wanted, like T star. That's the temperature he set for us. That's what he wants for a simulation. So he takes like T minus T star, and squares it, divides it by some relaxation thing, and he says he has kind of a differential number. He tries to like minimize that thing. That's kind of how his thermostat works. And also, he's got pressure, he's got the volume of the system, and he's got the number of kind of things in there. So he's going to end up with like a pressure more or less from those. Pressure would be like N over VT or something like that, right? So he's got a pressure, so he's also got the same thing as that P minus P star squared, and then divided by some tau differential thing. And he gets a differential for pressure. That's a baryostat. So he does his motions. He does all this, and he has drag coefficients and things that decide the velocities of everything. Then the bonds are connected by springs. Then so he can do this, and then after he's done with that, he checks if the temperature is right, and it won't be right because the temperature is going to fluctuate all over the place. Whenever it fluctuates, he puts this damping function, tries to get it back to the right temperature. And over time, he'll settle his temperature down, right? I mean, there's problems with these things. You can, by damping it that way, apparently, I haven't done this, but you can get what's called flying ice cubes. Okay, so you can get regions where this thing damps it down. So you have a cube, yeah, it's at the right temperature, but that whole thing moves as a unit and it's flying around your simulation. Right, so you can get a bunch of those cubes, and that's a failure of these the thermostats. The baryostats don't have that problem, but the thermostats do. So there's ways to get around that. So it's all been like trial and error. Everything here with the simulations is kind of trial and error. So anyway, so you can just kind of get a feel for that. What's going on with these things. Right, so there'll always be a series of energies. There's this dihedral angle, the rotational energy, that mapping, right? And he's got that mapped out with these cosine functions of the angles. He's got some kind of scheme to get the dihedral rotation energy. So he's going to be, the velocity is going to be like translational motion and rotational motion. Everything it could possibly, and then there's usually going to be like bending of the bonds and springing of the bonds back and forth, right? So you can put in any energy terms you want. So the spring energies are always going to be this, like E is something squared, right? So that comes from, I didn't send that over there. Right, so the energy term here comes from this. You have force is change in energy with change in position, right? And then that equals the spring constant times the position. So you have your spring. If you pull on it, the force it takes is proportional to the amount you stretch. It's a linear spring. Right, so the energy means is K spring times X dx, and then you want the energy is going to be K spring times X squared, times 2 or something. Right. So you're always going to have this thing squared. That means it's a spring. If you have energy is something squared, that's a spring. So he's got both a linear spring, and he's got a spring of this swing around thing. So this is the angular spring. So they're both, this is like theta squared, that's X squared. So he's got both kinds of springs in this thing. So that's kind of the simplest. So this should be simple at this point too. So he's got all the bonds, all the springs, all the angles, all the springs, everything's a spring. It's just like a simple spring. He's got this dihedral thing. It's got these potentials in it. And then these are the interactions. So he's got a system that's got 100, he's got 50 chains that are 50 length. And then when he wants to go big, he goes 100 chains that are 100 length. He's got two, in this paper, he's got two kind of setups for this, right? So this is called a 612 potential, the first part of this. So he's got sort of Leonard Jones potential. He's got a short range attraction and a long range repulsion, right? So it's going to be that thing where you have a dip and then it goes up. Then he throws in this charge thing, like Coulomb, QQ. He's got charge interaction. It's simple. You know, the thing is kind of simple. The guy Chen that wrote this paper didn't come up with this. But all he did was download GROMACS onto his PC. Literally, you could do this at home, right? And it would take you like a month to figure out how to download all the right parts, but anybody could do this anywhere, right? So this isn't something he doesn't have to know anything about this except maybe how to Wikipedia what OPLS is. You know, that's about it, right? No, literally, like I had someone did a PhD in computer simulations, right? And in this class, with a Polymer person, you know, wrote a whole like 300-page thing on computer simulations, asked him to write a simple like loop to do the random walk. You'd think that would be pretty easy. It's just like a do loop. They couldn't do it, like not at all. So people doing these simulations aren't really like, you don't have to be really good at programming. You have to be kind of good at patching together softwares. So it's kind of a funny thing. It's an odd thing. Anyway, so that's what he's doing here. All right, so he puts in this cutoff distance because you don't want to consider, if you consider a system of 100 chains that are 100 units long, then, and you're considering all the way across the box. So you have a box that you're simulating and it mirrors at the sides, you know. So you get to the side and then it repeats on the other side. So it goes to infinity, but you're actually just looking at one box. Anyway, so, but if you have that, so this R cutoff, it has to be at least the box size because you can't like go off into infinity like that. Energy would go off into infinity, but eventually it doesn't matter anymore if you're far enough away. The shorter you set this, the faster the thing will run. So he sets it to 12 angstrom, right? That's I guess some reasonable number that GROMACS told him to use, right? So, but that makes it run. If you make it too long, if you consider interactions too far away, it's going to take too long to calculate all the possible bonds. Then he sets some time scale for steps. So you see, you kick your things of velocity, they move a certain distance. And then you check the energy of the system with the temperature, with your thermostat and baryostat. And then you iterate that, right? So each one's going to be a time step. You know the velocity, so the velocity times the time step gives you the distance you travel, right? So he's got some reasonable time step, and then he's got some kinds of thermostats and a baryostat, and then he has some kind of decision. So you have to decide, well, when is it a reasonable system? Because you start with your bias, however you put it in. So there's some bias to it. It's not nature, or not whatever, computer nature. So you have to decide, like, when is it going to be nature? He decides when he reaches autocorrelation at 0.1. That also probably is in GROMACS or something. And then everything kind of stabilizes there. And then he does his measurement. He sets his thermostat to some other temperature and then waits 870 time steps, or I guess 435 time steps, and then he says that's the answer. So it's all kind of reasonable. He's going to get from that. He's going to get this persistence length as a function of position. So he's playing persistence length versus chain index number. So he gets that kind of upside down U-shaped thing. It's probably a name for that, but. And he's going to look at different tacticities, right? So he's got isotactic. This is syndiotactic. So it goes on, off, left, right, left, right. Then he's got these weird mixtures to see how that affects the chain structure, right? And then he's got it for polybutylene 1, also isotactic, right? And he does it for polyethylene. It's like everyone does polyethylene. I think the black one's polyethylene. So it just does that as like a check kind of. And then you can see, like, when he puts in these fancy mixtures, he gets really odd things happening. So that's kind of the interesting thing in this. And then this is how he calculates it. So he takes his chain. Right. So he takes his chain, like whatever it looks like, and he's got this vector R. So he's got R, that's a vector, and then he's going to dot product it with this R of wherever he is, like at position K. That's going to be this little R like that. Then he normalizes that by the absolute value of RK of R. Like, in other words, each step is of length R. So he's got this R to normalize that. This thing will give him LP, just kind of the average LP. So it would give you one number, right? But he's got 100 chains. So he goes to that K unit of every of the 100 chains, and then he averages that number over all the units of LK. And also he's going to be doing a time sequence on this. So you can look at, like, how does that thing change with the position, with the time. So he could do both. He does a position average, but he could also do a time average if you want it. And then he gets this LP that way. So I guess we'll have to talk later about how that works, like why that ends up being LP. We'll talk about that when we'll talk about persistence length, exactly how. So the Kuhn length is two LPs for a Gaussian chain. So you can kind of think of the Kuhn length, which is if you did your walk and you had steps of length LK. The persistence length is something, if you took your chain and you said, like, when does it break off at 60 degrees from the path of the chain, from the start to the end, that's LP, more or less. So if you take, your thing's going to be a squiggly line. I'm going to take this point, and then how far do I have to go until it's gone 60 degrees from whatever my start point was, and that distance is LP. Right, so it's kind of, it's not exactly that, but that's kind of what it is. Right, so there's two different ways to talk about this. You could say the chain is actually a series of steps of some length, or you could say it's a continuous ribbon, and you just talk about the curvature of it. So LP is going to measure the curvature. This is just this thing that is invented. The Kuhn length, right? So anyway, so it's that business. Let me go back over here. All right, so that's this thing. I mean, you can look at that. This thing is also mentioned in this paper by Binder. Binder's a pretty famous guy. I think he's retired, because I was at a thing with him a few years ago. So, but anyway, I don't know these other guys, but basically Binder's a pretty famous guy. He wrote a paper on definitions of persistence length. So he goes through that definition. I mean, you can glance at this if you want. You don't have to look at this. But the main reason this paper uses it is because the paper calculates, they do a Fourier transform of the structure, and they get the scattering function, and they use the scattering function to get the persistence length also at the end of the paper, but it isn't in the quiz, the homework thing. Anyway, so they get these kind of things. These are the input, the structure, and the output of these maps of persistence length versus position on the chain. And then so that's interesting in itself that you get. So you talk about, you're going to measure it with scattering to get this persistence length or rheology. It's actually so it's actually going to be a mixture of these weird. It's going to be the average of this whole thing, including the ends, including these little hills and valleys that show up, because there's some kind of distribution of these tacticities in the chain. So it makes it show up that there's a lot more complexity to it than just one number, right? So that's kind of one thing. And then this is his time. So he's doing the simulation to look at time. So there's isotactic, right? So I guess the main thing from this is that isotactic is really pretty random. This is the flipping of the dihedral angles, I think. Time of dihedral angles. So like how the thing is spinning. So they can spin. There's potentials that kind of hold it, that potential map, but over time for every index along the chain to 100, you can see they aren't holding it much time. So these helices are actually really pretty much flipping around all the time. They aren't really a helix at all. They're just like zipping along. When you make it syndiotactic, there's a lot less blinking of the lights. So things are happening much slower. So the syndiotactic holds its structure better. I don't think that was known before this paper. If it's true, you know, I mean, it's a simulation. You could say it might not be true, but basically that's kind of odd that the dynamics of the syndiotac is much slower than the dynamics of the. And when you mix in one syndio and an iso, then the syndio is like still really slow. So it shows up as like a slow car on the racetrack, you know. Then everything else is flipping like crazy, almost as if it was just the isotactic. So this mapping is kind of interesting. It's not a question on the thing, but then this is just looking at, in the end, like what's a mapping in general for these angles, and like what are the helical structures forming in it. And he gets that as a function of when he has a defect in the structure, and then like how that pans out. So it's kind of interesting. I mean, it depends what you're interested in, but you know, and he's got, anyway, that's kind of the end of the homework thing. There's more to this paper. It's not that long of a paper, but they did a lot, so that you can take that structure, and then you can do a Fourier transform. So you can take the so you have your whatever you had. It's a helix, or it's this thing, or it's partly helix, partly that thing. So you can take that structure and do a Fourier transform, which involves like an integral. You change it from real space to complex space. You have a real space mapping of the structure, like the positions as a function, or position function of x, and then you'll get like the intensity as a function of q, basically. You get the amplitude b squared. Right, so there's a way to, this is breaking down your structure into frequency space. Frequency being 1 over size here, because you aren't using time, you're using space. Right, so you get this frequency space map of it. So it means how many big blips do I have? How many little blips in terms of density, right? So that gives you this kind of the intensity, and that'll be always a decaying function of some form, usually log, right? Then if you know the structure of it isolated, you can take that structure and divide it by when it's organized. So the unorganized versus the organized, to get the ratio, that gives you the amount that's due to the organization. So it'd be like the diffraction pattern, I guess, more or less. So this usually has a peak in it because the organization involves things being near each other. And from that mapping, you can get the persistence length. You can get a lot of things, but persistence length is one. For one thing, you know that the intensity goes with q to the power 1, because this is like the mass, and this is like 1 over the size. And if it's a rod, the mass goes with the size to the power 1. Right, so that's a rod equation. So he plots. This is not in the homework, but he plots this S of Q times Q, which removes the 1. So he looks for where it's flat, and he calls that something I never heard of before. First off, you could just plot log of the two things and find out where it's linear, and that would be the persistence length. It would be kind of easy. But he does this structure factor times Q versus Q, and he finds out where it's flat, and he calls it a Holzer plateau, which I've never heard of before, but apparently it's important to somebody. Probably reference 61 would be where it's important. Probably Hoser, no, Binder. Okay, it's from Binder's paper, that thing. So anyway, so he gets that. That's how he determines the persistence length. He finds out where it's flat. And he says that's 2 pi over that Q is the persistence length. So that's another way that he gets it. He gets it from 2 methods. I didn't ask about this. Anyway, so he does that. So he does a lot in here. It's a pretty good paper. Oh, there's another paper too. We have 4 minutes. This paper was before that. And so this guy's doing 100 chains and 100 units long. This guy does 1 chain, and he's not doing molecular dynamics. he's doing, it's a Greek group from Athens, and they're doing Monte Carlo, which is kind of like, okay, so they're doing the same thing. The only reason to put this in is because he references it, and then he shows this plot of isotactic, syntactic polypropylene, and the numbers are different. Doing it this way, but this is a single chain. Okay, doing this Monte Carlo method. So let me just say what Monte Carlo is. So basically, this paper, we got 4 minutes. So Monte Carlo is like a gambling capital in Europe, right? So it's basically going to involve gambling. So you flip a coin. So you're going to have, in this case, you got your Newman projection. You have polymer, and then these R groups coming off. Let's see, this guy's only got 2, so whatever. So you can put in his tacticity, and then he has this rotational dihedral angle that you can spin around, right? So you spin that randomly, right? And then you check the free energy of the system. Usually it would be Gibbs free energy at constant pressure, but because in a simulation you have constant volume, so your simulation is in a box. The box doesn't change size, so it's constant volume. So use the Helmholtz free energy for A. So anyway, so they're kind of similar. Like you're trying to minimize it to get the state. So if the free energy drops because of your random motion, then you say yes, I take that. That was a simulation step. If it rises because of that, you say maybe. You don't say no. So that's where the Monte Carlo comes in. You say, well, it would be no, but I'm going to say with some probability of like 5% that it could be yes. So I'm going to flip a coin. I get a random number. The random number is below 5%. I take it. That allows you to let the thing evolve, because otherwise everything in the world will just go down to a single crystal and collapse down. So it wouldn't be very interesting. You just get the minimum free energy, which is a solid infinite crystal, right? So this allows it to kind of wiggle, right? It also, this probability is weighted by KT. So you can change the temperature, kind of changes the probability of acceptance. So you can go to high temperature and it'll be randomized, and low temperature, it'll settle down. So you can get phase separation with that. That was first done with magnetic moments, and it's called the icing model. When you do that. The icing model. And the method of doing it is called the metropolis, which was a guy's name. It was a Greek guy's name, in fact. This is a Greek group, so it's called the metropolis method. Anyway, so they're doing that. Usually you can do that in 2D and 3D. He's doing it in 1D. He's using this tacticity mapping of the chains and getting in line it to settle down and find out what the dihedral angle mapping is going to be, and also the so it's just another view of it, different ways to do it. So I think it asks you to like compare the two, and the numbers are different. So this is a single chain with 100 units. The other guy's got 100 chains with 100 units. He's not considering the energy of interaction between the chains. There's differences in the simulation method. They get the same answer, that isotactic's got a lower persistence than symbio. The qualitative answer is the same, but the actual answer is different. So that might tell you how much you should believe simulations, I guess. Like depends on the method somewhat. There's a lot. Anyway, these are two that are almost the same thing, doing it 2 different methods. Right? One, this is 2018. The other one's this year, like kind of this month. Right? So it's kind of interesting to look at that. Anyway, we're out of time, so that's good. Thanks. So if you need help with it, email me, whatever. So. I'm gonna kill this guy now.